Okay, so welcome everybody. So I'm going to be presenting a little bit about the technique that I learned during my PhD, and also some of the applications that we did. And so I'll start with a presentation of the lab that I'm coming from. So I'm from Canada. I'll go through the measurement technique. I'm going to actually put an emphasis on the measurement technique called deflectometry, and then eventually get into some applications of loading identification using the virtual fields method, and then show you some of the results from my thesis. So who am I? I'm from Quebec in Canada. I'm currently doing a postdoc at Loam, as a collaboration between the Loam and the GOS in Sherbrooke. And so my two supervisors on the Le Mans side, it's François Gauthier, and in Sherbrooke, it's Alain Berry. And so the subject of the postdoc is on so full field optical measurement techniques. So deflectometry, in my case, being applied to the characterization of acoustic black holes. I won't get into any detail on what acoustic black holes are today. I'm sure there's some people in the audience that know a lot more than me, and I still need to do my reading. I did my PhD defense at University of Sherbrooke earlier this year, and as you can tell from the thesis title, the identification of dynamic loading using deflectometry and the virtual fields method. Some of the slides I'll present to you today are some of the slides from my PhD defense, but I'm going to put, as I was saying earlier, more of an emphasis on deflectometry and the perspectives we see during the postdoc. So where is Sherbrooke? I'll do a little press for Sherbrooke University while I'm at it, because I'm still partly working for them. So Sherbrooke is actually about an hour and a half east of Montreal. And there, so you have University of Sherbrooke, which is a French university. There's about 40,000 students with cooperative programs in most faculties, so meaning that students can do internships directly with local industries. So it's known for its patent licensing and has a decent ranking and publication impact. And there you'll find the GOS, which is the acoustics group. Also a few facts about it. It was founded in 1984, and we're in the mechanical engineering department. There's about 40 to 50 people, and that includes the full-time professors. So whose names you might recognize here. And it's the largest Canadian academic lab in acoustics and vibration. And there's collaborations with the big labs in France, so at Le Mans and Lyon. The research fields are pretty broad. So I was more in the vibroacoustics side of things, but there's also materials research. Do I have a pointer here? I think I have a pointer. There we go. There. Okay. Yeah, so active control of noise and vibrations, and obviously ultrasound, so non-destructive testing, acoustic imaging, and wave field synthesis, and sound field studies. A couple of the infrastructures over there. So there's coupled reverberant semi-anechoic chambers. So for like transmission loss tests. There's an anechoic wind tunnel. Some equipment for sound field testing, so wave field synthesis and ambisonics. And some of the typical specialized equipment like a 3D laser vibrometer, and a few high-speed cameras. And so the high-speed cameras, that brings me well into what I'm here to talk to you about today. So for those of you who don't know what full field optical measurement techniques are, I like to think of it as if you're going to do a measurement in modern research, you usually need to do some analog to digital conversion. So you could use some digital acquisition hardware. So here you have, you know, a Bruit à l'équerre front end. You can probably get about 100 channels on there. With a 24-bit dynamic range and a sampling frequency of 25.6 kilohertz. Now compare that to a high-speed camera. So the sensor on the camera, so this would be a 1 megapixel high-speed camera. It's equivalent to having over 1 million channels. So light intensity sensors with a 12-bit dynamic range. And quite a decent acquisition frequency as well. And so keep in mind that you can boost this if you use less channels, so meaning less pixels. So now that we see that cameras are decent measurement hardware, or at least interesting in terms of the number of channels they can offer, so what types of cameras can we find? What types of high-speed cameras exist? And so this is a nice chart that's from 2016, which categorizes cameras based on their characteristics. So the size of the rectangle here is directly related to the size of the sensor, so the number of pixels. You can ignore the circles here. That's just to show the exposure time, the different exposure times. So really what you notice is that the cameras are grouped into two families here. So the family up here on the left are the high speed, and the cameras down here on the right are the ultra high speed cameras. So frame rate along the x-axis. And what we notice is that you really need to choose between either having so this is the record length. You can either have a lot of images at a lower speed, or very few images, so only a few hundred images at very high speed, so millions of frames per second. So in terms of vibroacoustic applications, really this is the family of cameras that we're most interested in, because they'll usually have certain type of so dedicated storage that's many gigabytes, and that allows you to take more images and therefore do frequency analysis and that kind of stuff. But we have to answer the question, so how can we use light to measure structural deformation, which is the goal here. And there are multiple techniques, so luckily people have thought about this. And so the technique I'm going to present to you today is called optical deflectometry. So it consists in observing the reflection of a printed grid. So it's printed and we glued it to just a wooden panel, and we're observing it by reflection on a reflective sample. So this is an aluminum panel that's been polished to a mirror. And so the observed image will be kind of a smooth version of the grid. And so by observing it with a high-speed camera, you can imagine that as the structure deforms, so as the mirror deforms, it's going to distort the image reflected so by the surface. It's kind of as if you were to bend a mirror in front of your face. You can see the image be distorted. And so the raw data is exactly as you would expect. So this is an example of a plexiglass panel being impacted at its center, and you can literally see deflectoral waves emanating from the center. But so how do we analyze these images? It's fairly simple, actually, using some geometrical principles. So if you imagine an initial state where the structure, the specimen is undeformed, and so you're just observing an undeformed version of the grid. Then say we look at one pixel, so a single pixel on the center on the sensor that's observing point P on the grid. As the surface deforms, so if we think of there being a local slope at the point M here, well then that ray will no longer be coming from point P, but from point Q. And so we can actually define that distance as being a relative phase, so a phase variation along the grid. And we can also define that same distance geometrically by noticing that if there's a slope d alpha at point M, then that would produce an angle of 2d alpha, which would then give you the distance between points P and Q. So by using these two relations, you can actually reorder this equation and find a really simple geometrical relationship between the phase variations, which you determine from image processing techniques, which then directly give you the local slopes on the surface. And deflectometry is quite original in the sense that it gives you direct access to the first derivative, so the first spatial derivative of the displacement. So it's a slope measurement technique. In terms of image processing, so it's a relative technique, as we saw. So you're always comparing a deformed image to a reference image. And you do a phase extraction procedure with a dedicated algorithm, which I won't go too much in depth today. But so it's called a phase stepping algorithm. And then you extract, so your phase along the X and along the Y direction for both the reference and deformed images. And then by comparing them, so taking the difference between the deformed and reference, then you get a relative phase. And in this case, it's a wrapped phase. So you need to use a 2D phase unwrapping algorithm. And once you do that, you get the phase, which you can relate to the slope using the geometrical relationship that we just saw before, and then do so either numerical integration or differentiation to calculate the quantities that interest you. And so just to compare with a tool that most people in either acoustics and vibration research are familiar with, so the Laser Vibrometer. So doing a measurement on an aluminum panel excited by an electrodynamic shaker at just a single frequency, we can see that we have a good comparison of the results for the displacement field, the transverse displacement field. And but the interest here is really what we gain in number of points with higher resolution, so only 2.1 millimeter separation between the measurement points on the sample, and especially the measurement time, since all points are measured simultaneously. But really where deflectometry shines is when you look at transient phenomena, since it's a space and time resolved measurement. So here's an example of an aluminum beam impacted at its base, filmed at quite a high frame rate, so 60,000 frames per second. And you can see that we see all the frequency content. So we can actually see the torsion in the beam. So there's a lot of information there for a measurement that only takes a few seconds. So there's some new developments in deflectometry. So some which I'm working on currently as part of the postdoc, and some which I have already worked on since my defense earlier this year. So one of the drawbacks, which you may have already noticed, is that for deflectometry, the surface needs to be reflective. So it needs to be a mirror. And that's probably one of the reasons why, it hasn't made its way into the industry yet. It's really stayed more of a research measurement. So some possible solutions. So one that we're looking at currently at NSIM is we ordered a bunch of different films, and we're looking at different combinations of adhesives and film thickness to see if there's a good way to filter out surface roughness, because even if a film has a really nice reflective quality, sometimes when you place it on an unpolished surface, actually you reveal all the defects of the unpolished surface. So the film needs to be thick enough to filter out the imperfections. Now, obviously, this can't work on a very thin structure because you're adding weight. It's like adding an accelerometer, whereas usually with optical techniques, the whole interest is being a non-contact method. And another option is infrared deflectometry. So you may ask, why infrared? Well, in the infrared spectrum, the interest would be that you would not need to prepare the surface at all. And so why would that be? If we recall, the two fundamental elements that you need for a deflectometry measurement is you need the surface of the specimen to be reflective, specularly reflective. And if we look at Rayleigh's criterion, actually the only thing that defines if a surface is specular or not is a ratio between the wavelength of the incident light and the surface roughness. So if we suppose that we're at an angle of where if theta is close to 0, then you can forget the cos theta. So basically, the wavelength needs to be at least 8 times longer than 8 times larger than the roughness. You can either achieve that by minimizing the roughness by polishing the surface, like we've been doing, or you can just choose a longer wavelength. So by moving to the infrared spectrum. And the other thing that you need for a deflectometry measurement is you need a high contrast grid pattern. And for that, we can take advantage of the emissivity ratio between different materials. And I have an example of a measurement that we performed earlier this year. So in this case, the beam on the left, so actually it looks like a very nice polished surface, but that's a mirror surface. On the other side, the side that the infrared camera is looking at is unpolished. So it's just bare aluminum. And what the camera is looking at is it's looking at this grid that we prepared, which is actually a second aluminum panel with a PLA grid that was printed using a traditional 3D printer, just a 0.5 millimeters thick. And by heating the assembly of the aluminum panel and the plastic grid, the PLA has a higher emissivity. So it'll show as a higher intensity. It'll show as a brighter element in the infrared image. So the grid pattern is revealed here on the right. And so we compared visible and infrared deflectometry. So visible was performed obviously on the polished side of the beam. And we see that we have a good comparison. So here this is the transverse displacement at the end of the beam. and we normalized it by the peak impact force, just to have comparable amplitudes. And we see that the signal is very similar, except that for the infrared deflectometry measurement on the bottom here, oh yeah, I didn't label them, but so on the bottom, this is the infrared, and on the top, this is visible. And in the infrared one, it's a lot more noisy. And that's simply because the infrared camera has a Stirling engine cooling system, which causes a lot of vibration. And therefore that vibration is transmitted to the images. So an important thing if infrared cameras were to be applied for this type of measurement is we need some sort of way to deactivate the cooling system just during the measurement. So yeah, I think the sensor is cooled to like minus 200 degrees Celsius or something, and that's what gives the sensor its sensitivity in the infrared range. So again, comparing the measurements, but now in the frequency domain. So we can see that the visible deflectometry measurement is a lot cleaner, but we still find the same resonance peaks in the infrared spectrum, just with a lot of noise. And then finally, comparing the operational mode shapes, we can see that the results both in visible and infrared compare well with the theoretical estimations. Even that you can see on the third mode, it may be hard to see, but there's actually an asymmetry in the third mode, which we see both in visible, kind of as a V-shaped lobe here, and it's exactly the opposite on the infrared map here, since that measurement was performed on the other side of the beam. So the image is flipped. And finally, so to compare the time resolved measurement of the two, so these are the synchronized videos of both here, let's see if I can take this off. There we go. And by pausing it at certain instances, you can actually see that it's the same. It's literally the same shape almost. Yeah. So it's quite interesting to see that the measurement is are in a good agreement between the two measurement techniques. So these are all results that are going to be published later this year, that are in review currently. Some other improvements that we can do is, so one thing I didn't go into depth in is that the phase extraction algorithm that we use, that's most used in deflectometry, has a requirement that the number of pixels that fill a period of the grid must be an integer. And that's because there's a 2D convolution that's done on the image, and basically the size of that convolution kernel is dependent on the grid period. So in the case so this is a grid that is that has 7 pixels per grid period. So basically, if you count from this black line to just this point right here, so the size of the convolution kernel would be 2n minus 1. So in this case, 13 by 13 pixels. So that usually involves either adjusting the lens on the camera until you just have the right magnification for that value to be an integer. Another option, possible solutions to this would be to have control over the grid. So to either display it on a television, or also I'll talk about maybe using a different algorithm that doesn't have that requirement. So this is something we're looking at currently at NSIM, is can we display the grid on a television for these measurements. So that would allow both faster prototyping, so meaning we don't need to print a new grid every time we want to try something new. But the real interesting thing would be automatic grid calibration, meaning that the image could change. Basically, the distance between the grid lines could vary for it to be exactly perceived as an integer by the camera. And so we did some preliminary tests by comparing different types of screens. For example, on the left is an OLED screen, which is nothing more than my cell phone. And on the right, this is the screen for my laptop. And we see two different types of technologies where the OLED actually has this streaming line through the screen, which is not very practical for the measurement. And that's because OLEDs actually produce each pixel produces its own light, and therefore blinks every time it's refreshed. And we can see that clearly the screen is refreshed in a line like this. In comparison, on the right side, this is a typical LCD with an LED backlight, which is powered by PWM, and that's why it's flashing. So we're looking for, and we think we found a television that doesn't blink at all. So that would be a good candidate for these measurements, so that we have a completely static grid. So I spoke about maybe using different algorithms. So this is also something we tried this summer. So by post-processing grid images, because as you saw, the grid images are basically black lines, but you can also see them as white dots all over the place. And that's where particle image velocimetry algorithms are interesting. So particle image velocimetry is usually used to measure flows. So either fluid flows. So by putting some homogeneous particles in the fluid, and then you basically track those particles with algorithms that then give you the fluid velocity. So what we tried is we tried two different magnifications of the camera lens. So we can see that in one case we are calibrated, and the way we know that is we can down sample the image by a factor of 8, and basically if we're exactly at 8 pixels per period, we should always fall on the same color, right? So we can see the color is fairly uniform throughout the image. So usually that's what we're trying to adjust to calibrate the measurement. And you can see that on the right, this is an uncalibrated case. So we purposefully uncalibrated the lens. So we changed the magnification so that here we see an interference pattern when we downsample by a factor of 8, because we have an interference between the 7.5 and the 8 that we're looking for. And then we use an open source PIV lab software, which is really great. So for any of you who are interested in doing any types of PIV analysis, this is a very nice piece of software that's free. And so we compared the traditional phase extraction algorithm with the PIV lab results. And the way that we did that is, so PIV basically gave us the, typically you think of PIV as giving you velocity because it's velocimetry, but basically it just measures displacement between two frames. And since it knows the time between the frames, it calculates the velocity. So we got the displacement here, the pixel displacements that I call P. And then this is divided by the number of pixels per period, but this is different. We can actually estimate it from the image just by doing a Fourier transform of the image. We can get the periodicity of the grid. So we can find n, and in this case, n doesn't have to be an integer. So in that case, PIV lab is insensitive to whether we are tuned to an integer number of pixels per period or a non-integer. And so these values, 8.06, 7.47, so these are actually NE. Sorry, I put NP here, but they're the same variable. Whereas with the traditional phase extraction algorithm, we can see that, well, since we have to give it an integer value, in this case both times 8, well, we bias the result, the test that is uncalibrated. So this was an interesting test. There's some more things on the horizon. So these are discussions that we're having currently. So options to do deflectometry measurements on a string, because traditionally systems that allow you to do measurements of both axes of a string, basically full field measurements on the whole length of the string, are usually very complicated, whereas this would be a very simple setup that would allow you. So in this case, we would only need a 1D grid because we only need the slope along the length of the grid, along the length of the string. And then using a mirror, we could get both the top view and the side view of the string. And in this case, the mirror would have to be pretty close because we need both views to be in focus. And this is another thing that is in development, not by us, but by Yves Surel, who is considered the father of deflectometry. And he's currently working on ways to apply deflectometry to curved surfaces, because it's obviously limited to a flat surface. You know, for the math to work out the way that I presented it to you. But there are other ways. So if you initially display, let's say, a regular pattern and then see how it is deformed on the surface, then you can actually compensate by deforming the grid. So in this case, this is a television showing the grid, so kind of similar to what we want to do. But so it's being used in this case to deform the grid so that it's viewed as being regular on the surface of the specimen. Obviously, this technique is a lot more complicated, and you need to know exactly the positions of all of the parts of the setup. But it's an interesting development. So now I'm going to get into, so let's see, it's 11:36. I think we're pretty good on time. So I'll get into some of the work that I did during my thesis, so which was to apply this deflectometry measurement technique to loading identification on structures. So a bit of background about loading identification. And I'm sorry, these slides are in French. I didn't have time to translate them all, but at least that may be better for some of you to read them. And so the objective here for loading identification is we want to identify the sources that are exciting a structure. So that can be for either doing stress analysis or fatigue prediction, or even vibroacoustic problems, so to know where the source of vibrational energy is coming from, for example. So certain problems could be either vibrations being transmitted to other parts of the structure, so you want to identify the source. And it could be also so surfaces that are radiating acoustically and producing noise that is uncomfortable. So for example, here is an example of a turbulent boundary layer. So a fluid flow on a surface, which then creates vortices that impact the surface, create vibration that then radiates inside the airplane. So you may ask, well, don't we have sensors for that? We have sensors to measure forces and pressures that act on structures. But the problem with discrete sensors is, well, they obviously depend on the nature of the excitation. So if you want to measure pressure, you usually use a microphone. For forces, you usually have sensors dedicated for that. And if you want to do a spatial measurement, like for example, for the pressure of that turbulent boundary layer, well, you need a whole array of them. So a lot of cabling and expensive acquisition equipment, and by placing your sensors there, you might be putting them right in the way, or you might be perturbing the excitation you're trying to measure. And so a few others. So either you can't access where you want to put your sensor, or maybe the sensors are too big, so you're averaging on too large of an area. So the proposed approach is to identify these sources indirectly. So do a vibration measurement of the structure, and then identify the sources from that. So the problem that we're trying to solve here is basically the vibroacoustic problem of some dynamic loading being applied to a structure, which we define by a model, which then responds, which then vibrates and then interacts with the fluid and can then radiate acoustically. In the case of a heavy fluid or a light structure, we'll say, the acoustic radiation can also have an impact on the vibration response. But we're going to limit ourselves to the vibration problem here. So basically, we know the structure. We need to have a model. We're going to measure the vibration, and then we need to identify what the loading is on the structure. And the interest of this is that it's independent of the type of excitation, as long as it produces a deformation. But the mobility of the structure will be important, because obviously if the structure is too rigid and your loading is not producing any deformation, well, then you won't be able to measure it. So there we go. Yeah. So we're going to resolve this the problem in the box, and we're interested in both plate structures and membrane structures. And in the case of the membrane, we might need to take into account this fluid structure interaction that I spoke about earlier. In the literature, we usually distinguish two types of methods, so inverse methods and identification methods. Inverse methods typically use more complex models, so either numerical or experimental models, which usually have a large number of knowns and thus require regularization techniques, because you're either doing matrix inversions or inverting transfer functions, but they allow you to work on complex geometries. On the other hand, identification methods will usually be based on an analytical model of the structure, and so are much easier to solve and analytically, and will usually depend less on regularization methods. But obviously they'll be limited to simple structures that have an analytical model. And so the type of method I'll be presenting to you today is an identification method. And so in terms of different identification approaches, we can note, so RIF, which has been developed here in Le Mans by Charles Bezra and his team, and it's gone through many iterations. So with a filtered variant and a corrected variant, and it's been applied to a host of different structures, so beams, plates, and shells. And it basically consists in, or well, the goal here is, say we have a plate with a certain distributed load on it. the equilibrium equation is given by, so the Love-Kirchhoff equation, for example, here, where we have the inertial term, the elastic term, and the external. So, so this is the unknown that we're trying to solve, and it would seem simple right away, except then we notice that the curvatures here involve second-order spatial differentiation of our measured displacement, followed by further second order, so another 2 differentiation orders. So we need 4, we have a 4th order spatial differentiation on the measured displacement, which produces or amplifies the measurement noise drastically. So it's typically a difficult problem, and that's why there's been multiple regularization approaches in order to make this work. Another approach that was developed around the same time is, but which was initially applied to identifying structural parameters, is called the virtual fields method. And so, on the other hand, it's based on the what we call the weak formulation, or the integral formulation of the equilibrium equation. So it's actually, this is the exact same equation, which we obtained by, you can imagine, just by multiplying by a virtual component here, which we'll call WV, so a virtual displacement field, multiplying the whole equation by WV and then integrating on the surface. So that allows us to, we've actually absorbed 2 differentiation orders into this virtual curvature term. So the interesting thing here is we've reduced our differentiation order by a factor of 2. And also this type of approach would be well adapted for, let's say, optical methods that have a large spatial density, because then these spatial integrals can be well approximated numerically. But obviously we'll need to choose appropriate functions for these virtual fields that we just multiplied in. So, okay, and these are the equations for a membrane. I'll just skip through that. So, and then this is, well, so you guys know about the vibrometer. So we're interested in using deflectometry. Yeah, I'm noticing the time, and I'm going to get to the results so that I don't hold you too long. So considering the definition of these virtual fields, basically the only requirement is that they must be continuous. So have continuity orders C1 in the case of the plate, and continuity orders C2 in the case of the membrane. And one interesting thing that we notice with the membrane equation is that these are, so the measured slopes, which we obtain directly using deflectometry, and this is the measured displacement. So in fact, this equation only contains a single spatial integration and no differentiation of the measured fields. So basically removes this susceptibility to amplification of measurement noise. The virtual fields are defined so using functions that are typically used in finite element methods. So they're defined locally on this small window. And this window basically scans the whole surface of the structure or of the data set, and identifies the you identify the force at the center of that window. Now, obviously, that means you can't identify along the edge. So that's one drawback of this definition of virtual fields. And using this formulation, you can either solve a force, so you need to basically approximate this this external force term, either by considering it being a punctual force in the center of the window, or being uniform pressure on the window. So to either solve for force or pressure. And there are other ways that you could do this, but these are the two approaches that I used during my thesis. And I'll skip through this. So this is another way of defining virtual fields that I developed during my thesis, and I basically compared the two types of methods. I think I'll just go straight to the results section. So I'll present identification results in increasing order of difficulty, I would say, or of complexity. So the first measurements that we did were just a electrodynamic shaker at a single frequency. And so the measured data from deflectometry gives us the slope in the X and Y direction. And we can't really see anything in the data. Actually, if you look very closely, you might be able to see there's something going on over here, which once we apply our identification approach, we see that in fact that is the point of application of the force. We did notice that with the virtual fields method, there was some spatial smearing of the force peak, so meaning that it wasn't as well defined as it was in reality, but that's an influence of the formulation of the virtual fields method, and the fact that you kind of have this spatial averaging on the virtual window. But by comparing the peak of the force with the force measured using the force sensor on the shaker, we see that we have a very good agreement between the measured and reconstructed amplitude. So leveraging the advantage of optical techniques, so being able to measure transient phenomena, we can measure the impact, hammer impact on a panel, and then reconstruct the force peak at a given instant. So I think, yeah, I already put an arrow here. So when I press play in 3, 2, 1, boom. So you should see in there. So you saw the force peak just at that moment, and then on the left, so that's the displacement that was measured by deflectometry, and you can see that so the displacement keeps going, but on the right, the force is properly being reconstructed as being 0 for the most part. And so if we just take a snapshot at the moment where the hammer impacted the panel, there we have the peak force, which if we compare to the signal from the impact hammer, we see that we have a good agreement between the amplitude, once again, and to show that the phenomena is really transient. And so this is an example of the signal of the transverse displacement at the point of impact. And so finally, since you have a full field view with optical measurement techniques, you can also measure multiple transient phenomena happening at different areas of the panel. So this is an example of 3 marbles being dropped onto the panel. And so we can plot, so these are the 3 different colors or 3 different positions on the panel. So in this case, our our frame rate wasn't quite fast enough, so we didn't really resolve exactly the peak of the force. So this measurement would have to be redone at like a higher frame rate. But what's interesting is we can actually condense all of the information of this measurement. So, this graph might look kind of wacky at first, but what's going on here is basically we have the spatial view with the positions of the 3 impacts. In the Z axis here, we have the force value of each impact. Now, once again, these aren't exact force values because we didn't really quite resolve the peak. But on top of that, what we can apply is, so this is a color map that designates the time that each impact occurred. So this impact followed by the center one, followed by this one. So it was just an interesting way to show how much information you get from full field methods. And then, so we went on to acoustic excitations. So an example of a diffuse acoustic field being generated in the reverberant chamber at the labs in Sherbrooke, and then a measurement being performed on an aluminum panel. And we had for reference an array of microphones. So what the results show is, so this is the spatially averaged autospectrum. We can see that we have a really good agreement, you know, up until about 500 hertz, except at the structural resonances. And so the virtual fields method is known to not perform well at structural resonances, because the problem of resolving the equilibrium equation becomes an ill-posed problem at resonances for you know, if you don't have a very high damping. And actually what we can see is that, so as the curve starts to take off here, it's actually because we don't have enough signal from the deflectometry measurement. So basically the acoustic excitation didn't have a high enough amplitude to cause visible deformation of the panel. So yeah, insignificant signal to noise ratio. So that's what gave us the idea to move towards membranes in order to have a larger mobility, or a greater mobility, in order to more easily see the deformation caused by, say, acoustic excitations. And so we proceeded to develop this membrane, so using a steel frame and a few different rings, tensioning rings. And so the membrane first had to be calibrated, and you can do that by looking at the different resonances of the membrane. And what's interesting is that the sound, or the sound speed, or the speed of sound in the membrane actually varies with frequency, and that's because, so at lower frequency, there's more mass loading. I think I'm getting that. Yeah, that's it. There's more mass loading at lower frequencies, so the membrane appears heavier. But as you go to higher frequency, you approach the in vacuo speed of sound. So it's a way of tuning. So you can actually tune and account for the apparent change in mass as a function of frequency. So yeah, that's pretty much what I just described. And this was a measurement that we did. So an acoustic excitation applied to the membrane. In this case, it's just, so it's a monopole source at a single frequency of 4,000 hertz. And we can see that we can properly see the wave fronts reconstructed on the membrane, but the amplitude is underestimated by a factor of 3. And we also did another measurement, so I'm kind of speeding through here. We also did another measurement with the membrane submitted to a turbulent flow. And so in this case, the membrane measurement was compared to a measurement using a spiral microphone array. And the flow velocity was 40 meters per second. And once again, we had the same phenomena of underestimation by about a factor of 3 dB. So this was nearing the end of my PhD, so I didn't really get much time to solve all of these issues. But some of the possible explanations are that, well, we're trying to compare a measurement on a pliable surface, a compliant structure, with one on a rigid substrate, so a rigid microphone array. It could be that the membrane wasn't well modeled, so maybe use a new model with the fluid coupling term, or maybe that we're actually seeing low pass filtering in the wave number domain by the membrane. So, and the only other example of somebody doing something similar is a recent PhD graduate from Southampton who applied deflectometry and the virtual fields method to identify air pressures. And he actually had to use finite element correction for his amplitude. So anyway, the conclusions about this. So what was interesting is that we developed an approach to identify any kind of dynamic loading on plane structures, so plates and membranes. And it was a full identification, so localization, quantification of the amplitude, and as a function of time, thanks to the optical measurement techniques. And what was original, also in terms of the membrane, is that there's very little literature on the membrane. We could only find one case where a membrane was used to measure a turbulent flow, but the measurement was only performed at a single point in space on the membrane, and only on resonance frequencies. So it could be interesting to study further, and also the development of other virtual fields. And finally, some perspectives of the postdoc I'm doing here. We're going to start by doing a benchmark of different optical methods. So compare traditional laser vibrometry with deflectometry, which is already, it's mostly about comparing different optical techniques, because we have here regrouped at NSIM specialists in the different techniques. So it's a good opportunity to see in an objective setting the advantages and drawbacks of certain methods. And eventually, the application of deflectometry to acoustic black holes to validate models and do different types of calculations from full field measurements. And then I don't know what this is, Developmentica. Yeah, okay, thank you. Are there any questions?
Merci beaucoup.
Merci.
Yeah, you have some question in the chat, but maybe some people first want to ask some question directly.
I don't have Zoom installed, so I can't see any webcams while I'm, I don't know if I should, here. Maybe I can look at the chat. Quelles sont les différences entre une grille régulière et un mouchetis en termes de précision? And so on. L'éclairage est-il monochromatique? OK. Alors, la différence entre une grille régulière et un mouchetis, donc, un mouchetis, ça pourrait être appliqué, effectivement. Donc, si on utilisait la même géométrie, donc réfléchie, ben là, il faudrait utiliser des algorithmes donc optimisés pour les mouchetis de style DIC, donc corrélation d'image. Mais je dirais en termes de précision, alors si tu demandes aux spécialistes de déflectométrie, en fait, ils diront toujours la déflectométrie est plus précise. Mais concrètement, ça dépend beaucoup de la qualité de la réflexion. Parce que si on n'a pas un beau fini miroir, ben là, on perd en précision, en fait. Alors, bon, et peut-être juste pour répondre à une question que j'ai souvent, c'est est-ce qu'on peut mettre la grille directement sur la surface ou est-ce qu'on peut mettre un mouchetis directement sur la surface? Et la réponse, c'est ben, non, pas si on veut les composantes hors plan. Parce qu'en mettant un patron dans le plan, ben là, on a juste accès à la composante dans le plan en regardant les déphasages de grille. Donc là, il faut aller vers une autre méthode, par exemple la photogrammétrie ou la DIC, où ça permet d'avoir une stéréocorrélation ou une perspective d'image où on peut ensuite voir le déplacement transverse. Mais donc, en théorie, les méthodes de grille sont plus précises, je dirais. Peut-être mais je veux pas... ouais, voilà. Puis c'est monochromatique, oui. Matrice Mac. Je ne sais pas c'est quoi Mac.
C'est simplement parce que quand on compare des formes propres d'un modèle et d'une expérience, ou entre deux
oui, ok.
on a fait une perturbation, il existe un outil qui s'appelle la matrice de Mach. Et dans le transparent 27, tu fais des comparaisons et tu dis ouais, ça marche bien. Et là, la matrice
oui.
de Mach, elle te permettrait de quantifier le truc. Voilà, c'est tout.
Non, effectivement, j'ai appris ça plus tard. Oui, mais c'était vraiment un papier plus appliqué, mais effectivement, une comparaison plus... voilà, oui. Ça aurait été mieux de les comparer de manière plus...
Et la question sur l'éclairage monochromatique, c'est quand tu es en lumière blanche, en fait, tu nous expliques après que la longueur d'onde a une importance.
Oui.
Et est-ce que tu as essayé de faire des mesures avec une longueur d'onde bien précise et qui ne soit pas dans l'infrarouge? Est-ce que ça améliore ça ou pas, à toi?
Alors, est-ce que tu pourrais me donner un exemple de source qui serait ben, comme une source néon ou quelque chose?
Exactement, tu prends une lampe qui est une longueur d'onde précise et puis tu travailles en monochromatique en fait.
Ben c'est intéressant. J'y avais pas pensé. Je dirais la raison pourquoi ça serait peut-être un problème, c'est que les caméras ont quand même donc ils ont une plage de sensibilité. Alors, en utilisant seulement une longueur d'onde, ben là, on vient couper la sensibilité sur toute une partie de la plage fréquentielle. Et en fait, l'intérêt des caméras monochromatiques, donc sans le filtre couleur ajouté, c'est qu'on garde toute la sensibilité, même une sensibilité qui descend jusque dans l'infrarouge. Alors là, on profite de toute la cloche de sensibilité au lieu de juste, une fréquence. Alors, non, c'est mieux pour l'intensité dans les images.
Je te remercie, Patrick.
Oui, pas de trouble. Est-ce qu'il y a d'autres questions? Oh, okay. Is the same idea as the television one? You could use a video projector to project the grid on your plate to measure. Okay. Donc, so yeah, so if the pattern is on the surface, then once again, you can only see, well, actually, no, if the pattern is projected on the surface, then you would need the camera to be off to the side in order to actually see the transverse displacement. And also you lose this natural amplification that you get from the reflection. Parce qu'on peut voir la réflexion un peu comme étant un bras de levier. Donc de la pente. Donc c'est vraiment ça. En fait, donc une petite variation de pente, ben, ça fait balayer sur la grille quand même une distance significative. Alors on a vraiment une amplification géométrique des phénomènes. Alors on perdrait ça si la grille était projetée.
Okay. Donc tu serais moins sensible.
Oui, ça serait moins sensible, effectivement. Ça serait plus pratique, je suis d'accord, si on pouvait projeter. Mais c'est vraiment la nature de la réflexion qui ajoute de la sensibilité à la pente. Ouais.
Ok, merci.